By now, you should have finished the lesson on the history of the structure of the atom. The lessons that you've learned from the previous scientists bring you to the conclusion that the atom contains a nucleus that is positively charged and extremely dense, and that the electrons are moving around the nucleus. Contrary to what Bohr thought, the actual accepted theory, the quantum theory, at this present moment, does not have the electrons moving around the nucleus in a two-dimensional plane. It is not the planetary model that Bohr had suggested. Instead, using Schrödinger's wave equation, we now believe that the electrons move around the nucleus in clouds, in particular regions that are three-dimensional. We call these areas the orbitals. This replaces the Bohr's concept of shells. There are 4 quantum numbers that are associated with Schrödinger's wave equation, which, by the way, was based on the idea that the electron is not a particle, but a wave. And because it's a wave, it must move along its wave pattern. This brings about the idea that there are particular sizes of orbitals that can exist. You can't have sizes that are in between these particular sizes. The size of the orbital is such that the waves will not interfere with itself when it moves back to its position after going around the nucleus once. So the 4 quantum numbers are meant to describe the position of where the electron is inside the atom. The principle says that we cannot know the exact location of an electron and its speed at the same time. So the purpose of the 4 quantum numbers is to give the general location of where the electrons are. More specifically, it'll tell us which orbital it's in and what spin the electron will have. The first quantum number is called the principal quantum number. Its symbol is N. This is similar to the energy level or the shell that you have recognized or come to know in the Bohr-Rutherford diagram. The principal quantum number describes the size and the energy of an orbital. So the values are 1, 2, and 3, and so on. The higher the energy level, the larger the size of the orbital, and the farther away the electron is from the nucleus. So for instance, principal number, quantum number 1, would be the same as this shell here in the Bohr-Rutherford diagram, or 2, 3, 4, 5, 6, and 7. This also corresponds to the period of the periodic table. So elements in the first period will have an energy level of 1, or a principal quantum number of n equals 1. Elements in the second period will have a principal quantum number of n equals to 2, and so on. The secondary quantum number has a symbol of L. This describes the shape of the orbital. It was noted that each of the shells in Bohr's theory can actually be divided into subshells. So the energy levels can be broken down into sublevels. These levels or subshells are known as s orbitals, p orbitals, d orbitals, and f orbitals. They have a subshell number of 0, 1, 2, and 3, respectively. The s orbital is a spherical shape. The p orbital is a dumbbell shape. Notice how there is a node in the middle of the p orbital. Electrons cannot exist in this node. The d orbital has this shape, and the f orbital is more complex. The s, p, d, and f orbitals can be found in specific locations on the periodic table, as shown on this diagram. Hydrogen has 1 electron, and you can see that the location of hydrogen on the periodic table indicates that it is in period 1. So what's the principal quantum number? N equals 1. You also see by the location of hydrogen that it is in the s block. So the secondary quantum number for hydrogen's electron is L equals 0. Remember that when we're talking about quantum numbers, we're describing the location of the electron. The next question that we'll look at is the electrons inside of helium. Helium has 2 electrons. The first electron's quantum numbers will be exactly the same as the electron found in hydrogen. The second electron's quantum numbers will be based on the location of where helium is on the periodic table. It can be found in period 1, so the principal quantum number will be n equals 1. The location of helium on the periodic table is still in the s block, even though it is on the right-hand side of the periodic table. The principal quantum number for helium's second electron is n equals to 1. The secondary quantum number for helium's second electron is L equals 0 to represent the s orbital. We're going to try to find the first 2 quantum numbers for sodium's last electron. So as you can see, it is in period 3 and in the s block. This means that sodium's principal quantum number for its last electron is n equals to 3, and the secondary quantum number is L equals 0. By now, you might have figured out that there is a quantum number for every electron inside of the atom. And most of the time when we ask you for the quantum numbers for a particular element, we're talking about the quantum numbers for that last electron inside of that element. Take a look at chlorine. The last electron in chlorine will be in period 3 and in the p block. We would say that the principal quantum number for chlorine is n equals to 3 and the secondary quantum number for chlorine is L equals to 1. Next, we have the magnetic quantum number. Its symbol is m subscript L. This describes the orientation of the orbital in 3D space. The allowed values for the magnetic quantum number is dependent on the values of the secondary quantum number. So it goes from the negative value of the secondary quantum number all the way to the positive value of the secondary quantum number. The magnetic quantum number describes the orientation of the orbital. In the example of the p orbital, where the secondary quantum number is L equals to 1, there are 3 orientations. It can go along the y-axis, or along the x-axis, or the z-axis. So this diagram shows you 3 p orbitals arranged in 3 different spatial orientations. The corresponding values are ml equals to -1, ml equals 0, and ml equals to 1. So this diagram is like a cartoon diagram of the actual probability zones that Schrödinger was trying to predict. In reality, the p orbital looks like this fuzzy drawing. In the d orbital, the shapes are slightly different. The secondary quantum number for the d orbital is L equals to 2. The magnetic quantum number is ml equals to -2 all the way to ml equals to 2. The orientations of the d orbitals are shown here in this diagram. The 3D orientation of the d orbitals and the f orbitals go beyond the breadth of this course. It should be noted that all of these orbitals overlap one another. As you can see from this diagram, when you draw all the orbitals in an atom, it gets quite complex. So when it comes time to draw 3D orbitals, we will only be focusing on the orbitals within the same energy level. The fourth number is the spin quantum number. The symbol is m subscript s. Each orbital can hold up to 2 electrons, and these electrons are different. One will spin in a positive direction, and the other will spin in a negative direction. There are 2 values for the spin quantum number, a positive half or a negative half. And so that brings us back to this diagram. This diagram shows us that if we know the location of an element on the periodic table, then we can describe the 4 quantum numbers of the last electron of any atom in the periodic table. So what would the 4 quantum numbers be for the last electron in sodium? Looking at sodium's location on the periodic table and using this chart, we can see what the 4 quantum numbers are. It is in the third period, so the first quantum number, the principal quantum number is 3, n equals 3. It is in the s block, so the secondary quantum number is L equals 0. Because it's in the s block, the magnetic quantum number must be 0. And as you can see at the top of the s block, we have a plus half and a negative half. And so this means that the fourth quantum number, the spin quantum number, is positive half. What about zinc? So the location is here. It's in the, this is a little tricky now. This first line of the D block is actually still part of the third energy level. So we call this n equals to 3. Even though it looks like it's n equals 4, this is still part of energy level 3. So the principal quantum number is n equals 3. The secondary quantum number is L equals 2 because we're in the D block. Remember, the S block is L equals 0, the P block is L equals 1, and the D block is L equals 2. The F block is L equals 3. The magnetic quantum number is going to be a positive 2. So as you recall, the magnetic quantum number has a value from the negative L value to the positive L value. But since we have two different types of spins, the positive half spin and the negative half spin, we arrange the magnetic quantum numbers in order from negative 2 to positive 2 for the first half of the d orbital, and we do it again for the second half of the d orbital. You'll see that the p orbital has the same thing. We have the magnetic quantum numbers arranged from negative 1 to positive 1 for the positive half spin. That's the first half. And the second half is the negative half spin. So we have negative 1 to positive 1 for the p orbital in the second half as well. If you look at the f orbital, the magnetic quantum number is arranged from negative 3 to positive 3 for the positive half spin and negative 3 to positive 3 for the negative half spin. So we see that the 4 quantum numbers for zinc are n equals to 3, L equals 2, Ml equals to positive 2. As you can see, that's where zinc is. It's on the positive 2 side. This is the negative half side of the d orbital. And the spin quantum number is negative half. That's it for quantum numbers. Thank you for listening.